Okay, this chapter will talk about the alkene reactions. Okay, so alkene reactions, sorry, alkene alkene reactions. Okay, so alkene reactions is the reactions of carbon-carbon double bond. So first, and brief, we'll talk about the synthesis. So synthesis mostly we'll discuss by elimination reactions. So if we have alcohol, generally tertiary alcohol, okay, and it react with a strong acid like H2SO4. Okay. So this will be eliminated. Okay. H and OH will be eliminated and it will form a double bond. So this type of reaction is more um, related, is confined to tertiary alcohols, and the reaction mechanism will happen via E1 elimination. Okay. And another important reaction, if you take a halogen, okay, and then you take a strong base, let's say here potassium hydroxide. So it takes this proton and chlorine will leave, and this happens via E2 mechanism. And it forms a double bond KCl plus H2O. Okay. So these are the two important elimination reactions that are used to make simple olefins. Now next, we'll talk about the reactions. Okay. So here the reactions will be different reactions of alkene. So first addition reactions. If we have an alkene, okay, then it can be eliminated easily by halogens can be easily added. So let's say if you have cyclohexene, okay, and you react with chlorine, it will be added pi bond will be gone and two chlorines will be added in trans fashion. Okay, so the product could be like this. So here and see this both the chlorine will be anti and it will be 50% and 50-50. Okay, so this one. Similarly, if bromine reaction with bromine will be also added, and this type of two products will form in 50-50 ratio. So these are racemic mixtures, okay, and these are the enantiomers. Similarly, bromine and plus another enantiomer will form. So let's see the mechanism with bromine. So what happens? Bromine atom by itself is electrophilic. Okay. Why? Because bromine is very has high electronegativity. So what happens at first? This will go and bromine will leave. Okay, I'm showing a stepwise process. You can show directly as well. So what will happen, let's say it makes bromine like this, Br plus Br minus, okay? And here is the positive charge. So this can react with this, and then it will form a bromonium ion. Okay, so this bromonium, so it can actually, this reaction happens directly. We can show this one in one step. Okay, so that just directly this one, and then this with this another isomer will form. Okay, and then it's both are same actually. Okay, because they are C2 symmetric, so these two are same. Okay, for in this case, so these are the meso compounds. So what happens now, this bromine can add to this one, so what will form, and this is an SN2 reaction, so it will go from the opposite side, so this will be the product. Okay, and now if this bromide ion reacts with this carbon, then what will form, that another enantiomer will form, so this bromine will go below and this will go above. So that's how this reaction happens as a racemic mixture, 50-50 of both the enantiomers are formed. So this reaction is when there is just bromine is used or chlorine is used. Now if chlorine or bromine is added with water, then the reaction is slightly different, and the product is the halohydrine. This reaction is called halohydrine. Halo means halogen, mostly chlorine or bromine, and hydrine, water. So the reaction, if we do with bromine and we take water, so only one bromine will be added, okay, and water, another OH will be. So not to mention that another isomer in this case will form as well. Okay, so what is the mechanism? The first step is same. So what is that first step? The same, the addition of bromine. Okay, so it will make bromonium ion intermediate. Now this bromine will leave as bromide ion Br minus plus H2O. In the reaction you have two things. So now because water is a better nucleophile, so this will react. Okay, or this carbon or this carbon, when it will react with this, so this product will form, and when it will react with this product will form. Okay, so this is bromohydrine. This product will be called, this product, bromohydrine. Okay, and this, instead of C here, we actually need just one bromine, another as a leaving group, it leaves. Okay, so if we use same with N-bromosuccinimide. Okay, N-bromosuccinimide, similar reaction will happen. See here, this part as a whole acts as another bromine atom. It leaves. So it will come here, this will go here, this will leave. And again, after the water reaction with water, we get the enantiomers of this one. Okay, so the reagent NBS in water or bromine in water will give you the same product. Okay, so another is the hydration reaction. So double bond, as we have seen in chapter 7, that double bond can be hydrated, means water can be added. The presence of a catalyst H3PO4, this acid catalyst, and generally it needs high temperature, okay, around 250 degrees Celsius. So what will happen? Just the reaction will happen via electrophilic addition of water. Okay, so this reaction is again is very harsh, so it's practically is not used much, and they're used for simple alkenes, not complex alkenes. Another that mild reaction that is called hydroxymercuration reduction. Hydroxymercuration reduction. Okay, so what happens? Mercuration reduction. I take mercuric acetate. Okay, this group is called acetate, CH3CO, CH3CO. So this is called acetate. In short, we write AC. So here another two acetate groups are attached to mercury. So here again, if you'll see the oxidation state of mercury here +2. So it is it's a kind of Lewis acid, electrophilic. So this will go here, this will leave. Okay. And you see the mercury has d orbital fill. So what happens? It will make kind of carbocation. Okay, here carbocation and Hg, I'm writing in short OAC. Okay, so mercury has more in d orbital, it has more electrons. So this again will make an like bromonium ion intermediate here, kind of mercuric intermediate, OAC. Okay, so OAC, this one here. So you see this one here as a carbocation. So it has more as a carbocation type intermediate. This one you can write same like bromine directly here from this, okay, in one step. Just I wrote this one to make you understand, okay. And then for water molecule is there. See, water will go here and the carbocation, okay, and it will form OH2, and this will make HgOAC. And then another water molecule will take this proton and it will be OH. And here you will be HgOAC. This is very stable, okay, stable. Even many cases we can isolate and we can take NMR and to characterize. So this one, when you take sodium borohydride, this will remove. So you need not to worry about this mechanism. So instead mercury will be replaced and hydrogen will come. So this is the product. So here you see this is the product. This product is same. The only difference is that it's very harsh condition. When we use mercuric acetate as reagent, the reaction happens without heating. Okay, so this is the reaction. Now here you see this, let's say, I'll give you one more example very briefly, because this reaction happens kind of carbocation type intermediate. So more substituted hydroxy group will form, because see this one here, carbocation type. So if you have mercuric acetate and water, and you take sodium borohydride in the second step, then what will happen? OH will go at the more substituted carbon. Okay, so keep in mind about this one. Okay, so hydration reaction. So these two hydration reaction. One more hydration reaction that is entirely different is that hydroboration oxidation reaction. Okay, so hydroboration oxidation. So now if you have, I'll give you this example here. Okay, methyl cyclohexene. So this methyl cyclohexene reaction, when we treat with BH3, and followed by H2O2, hydrogen peroxide, and basic condition, sodium hydroxide. So hydrogen, so this hydroboration oxidation, and this reaction also overall addition of water. Okay. So hydroboration, so what will happen? This reaction, both the hydrogen and OH will be added from the same phase. Okay, and not to mention for this achiral molecule, both the product will form, say hydrogen above and OH above, 50-50%. Okay, so they are racemic mixtures. So what is the important thing? Hydrogen will go to less substituted, a more substituted side, and OH will go less substituted side. And this reaction as a major product, this reaction is hysterically controlled. Okay, so we'll see the mechanism. So in the previous slide, this slide, we see this is both the addition of water happens according to Markovnikov's rule. Here the product is anti-Markovnikov's product. So what is the mechanism? First, see hydrogen, boron, and hydrogen, this added, okay, like this. So here you see, because the methyl group is big, okay, so hydrogen, this side will create less hysteric hindrance. If the methyl group, and if you put boron this side, then the methyl group will create more steric hindrance, and that's why it will not fit. Okay, so that's why this product, the syn addition, and that in such a way that it minimizes the steric hindrance. So if the higher this, I'm writing just only one initial, one isomer, and boron will be this. Okay, it has two more boron hydrogen bonds, so you can add two more olefins. So that is not always true, but it happens. Now the second step will be oxidation, hydrogen peroxide and sodium hydroxide. So you need not to worry about this mechanism. But first step mechanism you should know. Okay. Another important reaction is the hydrogenation. So what is the hydrogenation? Reduction reaction. So reduction reaction is the, if you take hydrogen, okay, and suppose you have methyl and hydrogen. Here you need the palladium charcoal. Okay, so palladium charcoal as a catalyst, palladium catalyst in charcoal, and hydrogen will react, and then the reaction again will happen in a syn fashion, that both the hydrogens will go on the same side. Okay, and another isomer will form. Okay, so there will be 50-50%. So what happens here, the palladium is a big atom, okay, like this. And when hydrogen and palladium is treated, hydrogen is trapped in this small, like hydrogens in voids. They are called voids, okay? And those are called occluded hydrogens. So suppose this is a one surface, okay? And hydrogen atoms are there. Just we are writing, suppose here, okay? So, okay. Okay, so this is the, if we take an osmium tetraoxide and NMO and methyl morpholine, so the double bond is converted into OH. So it's a 1,2 diol, 1,2 diol, okay? And this is also called vicinal diol, the product is formed. So the mechanism of this reaction is like this. It's a concerted reaction, okay, Diels-Alder type reaction. See here, see this will go, so it's like a kind of diene, not actually diene. So two double bonds are here, this will come here, this will go here, so it will make cyclic intermediate. I'm writing only one isomer, okay? And from here it is hydrolyzed with water, it's hydrolyzed to this, and with NMO. NMO is hydrolyzed this. and the osmium tetroxide is regenerated. Okay, so it's used as a catalyst. This reaction is very efficient. Just we need even 1% osmium tetroxide is enough for the reaction. Another is the ozonolysis. So ozone, if we react with ozone O3 and then treated with a reducing agent, zinc or dimethyl sulfide. So what happens? This double bond will be chopped here, cleaved. Okay, so we'll make a dicarbonyl. So what is the mechanism? This one, oxygen like this. Okay, so oxygen will add to the carbon, and this will go here, and this will go here. This is also all these three reactions that happen simultaneously. So this is called concerted mechanism. All these bond formation breaking happens simultaneously. And this intermediate will form. This is called molozonide. Okay. Again, further steps happens. Don't worry about that one, and it will form like this. Okay, and when we react with a reducing agent, this is called ozonide. And you react this one with zinc, it will form the dicarbonyl compound. Okay, so this remember, this is the reaction, ozonolysis reaction. Another similar reaction is the KMnO4 oxidation. Okay, so it's a very strong oxidizing agent. So if you have this compound, so it's a very good example here. This will be also chopped like ozone here to make 2 oxygen. In addition, what it will do, it will change the hydrogen to OH. So easy to remember, okay? It will make a carbonyl like here. You see this one here, carbonyl. So here you have CH3. It will not do anything to the attached CH3, but the hydrogen. So you will have carbonyl like this one is ozone, and the hydrogen will be converted into OH. Okay, so this is the example of this reaction. Now suppose with the KMnO4 reagent. Now suppose if you have like this compound, 2 hydrogens are here. Here you have 1 hydrogen. So it will be chopped here. So KMnO4, and then this will make OH, see this H. Okay, and here you have 2 H's, so carbon, and 2 H's will be OH and OH. This is nothing but bicarbonate. Bicarbonate, it decomposes to carbon dioxide and plus water. So this is same reaction that happens in the soda bottle that causes fizzing. Okay. Okay. Another, the last reaction in this chapter is the carbene addition to a double bond. Okay. So what is a carbene? Carbene is carbon with two bonds and two unpaired electrons. And this is called carbene. It adds to a double bond very efficiently via syn type addition, and it will add from the same phase. Okay. Carbon, and you'll get this cyclopropane type product. Okay, so two reactions in this to remember here. If you take chloroform and a strong base like KOH, okay, this will be converted into carbene and it will form this product. I'm writing just only one isomer, okay? Both will form in 50-50. This one. So how the carbene is produced in this case? So remember, this is the chloroform structure, chlorine, chlorine, chlorine. So this hydrogen is fairly acidic. So KOH can react with this. It will form a kind of anion. Now, as soon as the anion will form, one of the chlorines will leave. H2O, here you have potassium. So what will happen as soon as chlorine leaves in the form of chloride? So you have only two chlorine and this is the carbene plus KCl. And this carbene will add, okay, as shown here. Suppose here you have carbon. So here it has two attached, two chlorines are attached. Okay, and then without chlorine, just the hydrogens will be also helpful. Okay. So in this case, if we have, just remember the reagent, if we take diiodomethane, and zinc copper couple, then what will happen? It will just form simple cyclopropane. This one, and another plus another isomer will form. Okay. So this is called Simmons-Smith reaction, and this is a stereoselective reaction. This will form.